Good morning. Today, I'd like to talk a little bit about the relationship between these double integrals we've been looking at and volumes in three-dimensional space. To begin with, I want to remind you of what went on back in Calculus 1. The area of a rectangle is its horizontal length multiplied by its vertical height. One of our original motivations for developing the idea of an integral was if we have some function y equal f of x, where the f of x is positive on the interval from a to b, if we wanted to calculate the area of the region under the curve above the x-axis from x equal a to x equal b, we had a strategy for developing this idea. Our idea was this. We'll take the interval of numbers from a to b, divide it up into smaller pieces. Call the horizontal width of one of those pieces delta x number I, and I'm going to approximate the area under the curve that goes with this one subinterval by the function value at some representative number, ci, multiplied by the horizontal width. Then we add up all such estimates, and to make the estimates better, we take the limit as all of the delta x's tend to 0. If this limit exists, we made up a new name for it, and if it doesn't, then we say that this new symbol doesn't exist. The name that we give to this limit of sums is definite integral from a to b of f of x dx. And in the case where f is positive, we identify these individual terms as approximately areas under the curve that go with a given chunk on the x-axis. If the function isn't always positive on the interval from a to b, though, more care must be taken. Thinking about these sums, if I'm looking at a place where the function value is positive, like this place, for instance, then delta xi times f at ci will be the length across the bottom times the vertical height. That number will be positive and is an approximation to the area beneath the curve above the x-axis that goes with this chunk. But on the other hand, if the function value were negative, like here for instance, the quantity f evaluated at c times delta x is going to be a negative number times a positive number, which is negative. F at ci delta xi for rectangles like this is a negative number. It's the negative of the area between the x-axis and the curve. If I were to add up many such things, when I'm over here, I'll be adding up positive terms. When I'm over here, I'll be adding up negative terms. What I'll end up with after I take the limit is the amount of area above the x-axis minus the amount of area beneath it. So when I calculate the integral from a to b f of x dx, what I'm actually calculating is the area of region 1 minus the area of region 2. This number could be positive if area 1 had more area than the other. It could be negative if the amount of area indicated with the 1 was less than that of 2, or it could even be 0 if by chance the amount of area above and the amount of area below were equal to each other. For instance, the integral from 1 to 3 of x minus 2 with respect to x is easy to calculate using the antiderivative method. An antiderivative is 1/2 x minus 2 squared, and when I put x equal 3 and x equal 1 into this, here I'll have 1 squared, which is 1. Here I'll have negative 1 squared, which is also 1. 1/2 minus 1/2 is 0. This doesn't mean that there's a region of the plane that has area 0. It means that the amount of area above and the amount below are equal to each other. The integral from 1 up to 2 will be negative. That integral is the negative of the area of this first triangle. The integral from 2 to 3, though, will be positive. It's the area of this triangle. Area above minus area below. In this case, those two areas work out to be the same, so I end up with 0 for an answer. Moving up into 3 dimensions, imagine I have, say, a rectangular shape, maybe, or some other shape in a plane. It's got some area associated with it. I'm going to take every point in that region and move it upwards a certain common amount called the perpendicular height. The volume of a shape like that in three-dimensional space is the area of the base multiplied by the perpendicular height. To continue the analogy, imagine that I have a function f of two variables, x and y. I think about its graph, z equals f of x and y. For the moment, I'll assume that z is positive, so that all of the points of its graph are above the xy plane. I'll have some region down in the xy plane, and I want to think about the set of all points in three-dimensional space that are contained within this region and then lifted up in a perpendicular direction until it hits the surface z equal f of x and y. I'd like to think about the volume of that three-dimensional shape. How many cubic centimeters of plastic would it take to make this shape on a 3D printer, for instance? Think of dividing your region up into a large number of smaller ones. Pick one of them to look at. Say that one. In the XY plane, there'll be a certain amount of area to go with it, the area of the base. And I'm going to sit here at z equals 0 and go all the way up until I hit the graph that I'm interested in, the place where the z coordinate is f at xi, yi, where xi, yi is a representative point within chunk number I. The perpendicular height will just be the function value that goes with that. So the volume of chunk number I of the solid shape is approximately f at xi, yi delta A number I. I'll add up all of those estimates to get an estimate for the total volume of my solid shape here. And then I'll take the limit as all of the sub-pieces shrink down to points. This should give me the exact volume. Of course, by this time we've played this game enough, you recognize this as the definition of something. We recognize this as the double integral over region R of the xy plane of f of x and y integrated with respect to area in the xy plane. We could then, in a nice situation, use Fubini's theorem to calculate this integral. If function f is sometimes positive and sometimes negative, the same idea as before holds. The double integral will be the volume above the xy plane minus the volume beneath. If we stick to functions that are positive for the xy's we're interested in, then that's not a problem for us. So let's find the volume beneath the graph of z equals x squared plus y squared above region R, where in region R, the x can be anything from 1 to 2, and the y can be anything from 2 to 3. I've raised this up a little bit, hopefully to make the picture a little clearer. I'm going to have a square in the xy plane, and all of the points that are above that square but no higher than the z coordinate on the graph of z equal x squared plus y squared. The volume is the double integral over region R of f of x and y, which in this case is x squared plus y squared, integrated with respect to area. Because region R is vertically simple and also horizontally simple, we can use Fubini's theorem to write this double integral as an iterated integral. Then we'll do the inside integral first, then we'll integrate the result from x equal 1 to x equal 2 and have our result. After finding the inside integral, we have to integrate this, x squared plus 19 thirds, from x equal 1 to x equal 2. The result will be the volume that we're after. However, this integral is straightforward to do. After the calculations are done, we find out that the volume is 26 over 3. As another example, let's look at the region R in the xy plane in the first quadrant, starting at x equals 0, ending at x equals 16, meaning that the y is going to go between 0 and 4. I want to look at the region above the x-axis below the graph of x equals y squared. The function that I want to integrate is going to be f of x and y equals 1 plus x plus y, meaning I'm going to be calculating the volume of this shape. It's got a parabolic base, flat on two sides though. Vertically, there are straight lines, and when I intersect with this plane, I slice it off at an angle. I'd like to know what the volume of that is. So the double integral that I have to do is just this one. If I want to convert this into an iterated integral, I have to decide which variable that I should put on the outside. To begin with, just looking at the shape of the region, it's easier to describe everything in terms of y. In particular, I'm thinking about this x equals y squared. If I wanted to express stuff in terms of x, the y variable would be the square root of x. That might make things more difficult to integrate. So for my first try, I'm going to look at the integral on the outside as being with respect to y. That variable can go from 0 to 4. Given a y number somewhere between 0 and 4, the x numbers that go with it in the region can be as large as 16. This is true regardless of what the y value is. So for the inside integral, the upper limit of integration will be 16. On the other hand, for the given y value, the x value has to be at least as big as the x coordinate on the parabola, or bigger, all the way up to 16. I need to write down the x coordinate of the point on the parabola, x equals y squared. Obviously, that's going to be y squared. As usual, we'll do the inside integral first, and then integrate the result with respect to y from y equals 0 to y equals 4. Working out the inside integral is straightforward. Now we have to do the outside integral. And becoming lazy at the end, the double integral works out to be 558.9 and then 3 repeating. Hopefully, this is enough to get the idea across without going on too long. I hope everyone's having a good day, and I'll talk to you again soon.